Hello and welcome back. We're going to have another problem here, and this is a continuation of the last problem, but you don't have to watch the last video to figure this out. We're going to figure out, last time we figured out the maximum distance traveled on the first bounce. This time we're going to figure out the maximum height right here. So how do we, if we are given the initial angled velocity and theta, how do we figure out the maximum height? And we're going to write this in equation form, or variable form. We're not going to use any constants. Well, I guess other than g, this is actually important. We need to write this down. There we go, 9.8 meters per second squared. We're going to use g as the gravitational, the acceleration due to gravity on Earth. And there's no air resistance. We're going to ignore air resistance. All right, so the key to this problem is to find the right kinematic equation. I'm sure you guys know what these are, and we're going to only choose one, okay? We only need one of them. We don't need two or three. So pick one, whatever you think is the correct one, whatever you think is the best used to solve that problem. Is it A, this one? We are solving for maximum displacement, and this one doesn't have anything to do with displacement. This is just final velocity, and we're not going to need that. So we're not going to use A. A is kind of, and we could probably use A with a combination of others, but like I said, we only need one to figure this out, so we're not going to need A. B, well, this one is good. It has displacement, but it does have time. The thing is, there's actually something we can do to figure this problem easily, and we don't need time. But we're also given G, which is very useful, and there's no acceleration here, so I don't think this is going to be very useful here. Here we go. We have the acceleration. We have the initial velocity, which we know how to solve. We got displacement, but same problem here. We have time. We don't need time. We can ignore time. We're not here to solve time, and we don't need time to solve this problem. And this is the last one. Now, I've just heard, this is a one not a lot of people talk about. This is a kind of unknown equation. Like, I heard teachers sometimes say there's only three kinematic equations, which are these three, but they never really mention this. But this is actually a very useful kinematic equation, and you do need this to solve some problems. And this is actually the equation we're going to use, and it's going to solve our problem very easily. Why? Because of this final velocity thing. We have the initial velocity. We can figure that out easily, and we're given the acceleration, and we want to solve for displacement, which is perfect. Now, what do I mean by final velocity, right? We don't know anything about the final velocity, which is kind of a trick question. I kind of gave you a trick question because I didn't give you anything explicitly about final velocity or how to solve it. And there's no mention of it here. Well, the key is, if you recall from last video, when we were trying to solve for the maximum distance, the special thing about this point was that displacement was zero. No matter what VI or zero or theta is, the moment it hits the ground, the displacement will be zero. The vertical displacement will be zero. The horizontal displacement would be something. And that's what we were trying to figure out last time. But this time, we want to find the maximum height. Now, I want you to tell me what's special about this point right here. What do we know about this point? Even if VI or theta or G is different, what do you know about this point? What's something that's always going to be a given, no matter what constants there are? Well, the key was our final velocity thing here. That was the trick question. The final velocity here, or the vertical velocity, would be zero. Just think about it. As acceleration is always applying a downward force. That's the G. That's our G. That's our acceleration. And the initial velocity gave us an upward force. So here we can have it's kind of a very crooked arrow. Oh my god, that's terrible. Hold on, I'm gonna pause. Okay, good enough. Well, yeah, see, this is our arrow. This is our vertical initial velocity. That's what we did last time. We split it up into vectors. Well, this vertical initial velocity will start shrinking because of G, because of acceleration. It is deaccelerating. So at first it starts off big, but as time goes on, it gets smaller and smaller and smaller until it reaches this critical point where it is zero. Think about it. It is not moving at all. See how the velocity, the slope is getting slower and slower. That's because at this point, the velocity stopped being positive, it is now negative. So after this point, it's going to start going down until it reaches this. And as you can see, this should create a perfect line on a graph. If we graph this, something like this. See, this is the 0 axis. It should cross over those points. Okay. Well, we have another terrible drawing, which is bad. Let me fix that really quickly. Okay. So as you can see, this is 0, and we can say this is the final velocities, and this axis is the change in time. Well, not really change in time, because this is actually just a time axis. The change in time would be if we're looking at this point and this point, you know, at any 2 points, from 2 points. Usually the initial time should always be 0, but we call it change in time because we should. Anyways, as you can see, yes, the velocity is sloping downwards, and it hits that critical point. And that critical point is what we want to figure out. That's where our maximum height is. And we can use this equation right here. So we know that the final velocity has to be 0 at the maximum height. That's what we know. And yeah, we can just solve it. So the maximum vertical displacement is equal to 0 squared. So I'm squaring it so you know that this is the final velocity here, minus the initial velocity. Now in this context, we have the vertical initial velocity squared. That's what this was. All over negative 2g, because g is pointing downward, so we have to make this a negative. Because we kind of defined it as a positive number here, but we want to make it negative because the acceleration is pointing down, and usually down is negative. So now we can simplify this a little bit. So now we have VI y squared all over 2g if we simplify this, because these turn into a positive and 0 goes away. Now, remember, if we recall from last time, we defined VI, the vertical, we defined the vectors as I don't really know how to say. We defined the vectors using the initial velocity, angle of initial velocity, and the angle. So, you know, it's a lot easier because usually you're just given the initial angled initial velocity and theta. You're not really given these vectors, but you do have to figure out these vectors in this equation. So we can say, using some basic trigonometry, we can say that it is equal to that. The angled initial velocity times sine of the angle that it is thrown at. So now we can plug this in. We're kind of running it out of room here. Right here, perfect. You have some space. So this is it. The vertical maximum displacement is equal to the angled initial velocity times sine squared theta all over 2g. And this right here is our equation. This is what we use to find the maximum height of thrown objects. Now, I didn't really talk about this last time, but you can tell me at what angle will this give us the maximum height it can possibly be. If the angled initial velocity stays constant and you can change the angle, at what angle will this reach the maximum height? And hopefully you would get the right answer in this context. I'll tell you what angle for fixed initial velocity, what angle it has to be for the maximum distance, and that's 45 degrees because of how the equation works. If you recall from the last video, if you have the equation written down, it is 45 degrees for the maximum distance, but the maximum height, it is different. So hopefully you can tell me that. All right, thank you for watching. Hope this helped. Hope this helped you find the origin of this equation.